Hi everyone. In this video, we're going to go through section 7.4, exponential equations and growth. In this section, we'll look at a different type of growth that is not linear, it is not quadratic, but exponential growth. And we're going to use exponential equations to model that growth and solve exponential equations using something called the log function, which you may remember from some high school course in the past, but even if you don't, that's okay. We'll just get a brief overview of how we're going to use this fancy log function in working with exponential equations. We will start out with an example where we're investing $1,000, and throughout this section we'll refer to that as the principal, the amount that we invest, into an account that pays 8% interest per year. All right, and so after the first year, how much money are we going to have? Well, what we'll do is we'll take 8% times $1,000, and the way that I would type that into my calculator is 0.08 times $1,000 is equal to $80. Add that on to the $1,000 that we started out with. 1,000 plus 80 is 1,000. Whoops, I wrote that wrong. 1,080, 1080. There we go. Dollars. Okay, so after the first year, we've made $80. Pretty good deal, right? And after the second year, so let's do that same thing again. Now I want to take 8%, but it's not times 1,000 anymore, right? After the second year, we've already made that $80 during the first year, so we're going to take 8% times 1,080, the way that I type that in my calculator, 0.08 times 1080 is equal to $86.4. $86.40. We made a little bit more interest because we had a little bit more money in this account. We'll take our 1,080 that we started the year with, add 86.40, so plus 1,080 in my calculator, and that is equal to $1,166.40. So that's what we have at the end of the first 2 years. Every year we have a little bit more money, so we make a little bit more money in interest. Moving forward into the future, we would make similar calculations, and that process of going year by year and earning more interest and more interest on top of what we earned previously, that process is called compounding. It's compound interest. And we have the first 2 years that we already investigated, and also then what would happen the third year, okay? And notice I took the 0.08 times 1,000 and then added on the original 1,000. If I take that $1,000 times 1.08, the answer is 1,080. The 1 in the 1.08, that represents the step of adding back the $1,000. Or if I take 1,000 times 1.08 times 1.08, that represents the first year is the first 1.08, and the second year is the second 1.08. Okay, so we can that's how we take that process from the previous slide and create ultimately what is a formula on the next slide. And that formula looks like this, although my exponent got a little bit messed up. So let me rewrite this compound interest formula. It looks like this. A equals P times 1 plus R, and that's raised to the nth power. The n is the exponent. P is called our principal. Let me highlight that. P is called the principal. R is the interest rate, and n is the number of years. And then the A, the capital A, is the amount, the final ending amount that's in your account. And one other point that I want to make in this is that the R, that interest rate, is in decimal form. Decimal form. So that if I have 10%, that is equal to decimal point 10, or 72%, that is equal to 0.72, or 8%, like the previous example, is decimal point 0.08. Okay, so we have to make sure that we convert our rates, our interest rates, to decimal form. So let's go back to the previous example of investing $1,000, and let's take a look at what happens after 30 years. $1,000 We're earning 8% interest every year, and I want to know how much is in my account after 30 years. So I'll start out by rewriting the formula. A equals P times 1 plus R to the n, and then substituting 1,000 is the principal, 8% is the rate, but I'm going to write that as 0.08, and n is the exponent, the 30 years, the amount of time that's passing. All right, so first I'll condense what's inside my parentheses to 1.08 raised to the 30th power, and then let's type that into our calculators. 1.08, raise it to the 30th power, and then multiply by 1,000, and holy cow, we earned a lot of money. 10062.656, but when I round this, and then it keeps going in my calculator, 65689, but when I round this, that 6 takes the 5 and bumps it up to a 6, so 66 cents. We always round money problems as though they are money. So we have that original $1,000 has compounded and become, the interest has compounded over 30 years and has become $1,062.66. Ooh, $10,062.66. We made a lot of money. That compound interest formula is just a specific application of the general exponential equation. Okay, so that this exponential equation, a times b raised to the x power, the x is in the exponent, my unknown is in the exponent. It's not the base anymore like it was in the quadratic equation. Okay, that's called an exponential equation, and that's the general topic that we're looking at in this section, but specifically as it relates to money, because that's a good application of it. All right, so let's look at another example here. We're going to model population growth with an exponential function. All right, so let me highlight the important stuff. We've got the year 2014. The U.S. population was approximately 319 million people. Growth rate 0.6%. And if that growth rate continues until 2053, from 2014 to 2053, what will the United States population be then? Okay, so we've got to do a little bit of work here before we substitute into our formula. Okay, and the first thing that I want to write down is 0.6%. If I convert that to decimal form, it's 0.006, right? So we take the decimal point and move twice to the left and fill in my 0 there. If you are not sure about that, if you don't like doing it by hand, you can take 0.6% in your calculator and divide by 100, decimal point 0.006. The other thing that we have to figure out before we can substitute into our formula is 2053 minus 2014. How many years later is that? 2053 minus 2014 is equal to 39. So 39 years have passed. That's an important thing because that's the exponent that we need to substitute into the equation. All right, so now we can do our substitution. The formula again, A equals P times 1 plus R to the n. And I'm going to plug in the 319 million. That's my starting amount, my starting population, the principal investment if we were talking about money. We're talking about population in this one. 1 plus R 0.006 to the 39th power. All right, and that I can just type in my calculator all in one step if I want to. 319 million times 1.006 raised to the 39th power. Okay, if you want to put the 1 plus 0.006, you got to make sure you use that parentheses. Okay, but if I type that all in, let's see, I got 402.82, etc., which I'm going to round to the nearest whole in this example, since my 319 was to the nearest whole. So that would be 403 million people. That's a lot of people. 403 million people would be the population of the U.S. in the year 2053 if we follow that same growth rate of 0.6% every single year. We would pass 400 million people. Whew, that's a lot. Now, here's where we're going to talk about something called logs. It's short for the word logarithm. We're not going to go into a ton of detail with the log function. You might encounter in some other math classes if you need to take them, but I'm just going to give you a surface level explanation of how we use logarithms, when dealing with exponential models. So we're going to use it to find the time, when we're solving for the time, the variable up in the exponent, that it takes a quantity, to find the time that it takes a quantity that is growing exponentially to double. That's what we're looking at, doubling time. The function, the log of a value, returns the answer to the question, what power n must 10 be raised to in order to get a value of a? That's what the logarithm does. It answers the question, what is the exponent that I need to get this certain value a? And the way that it does this is using this really important property of logs. When I have the log of some value raised to an exponent, this property here says that that exponent can come down in front of my log term like that, and we can rewrite that as multiplication. So the exponent drops down and it turns into a multiplication problem. Ultimately, you're just pushing a button in your calculator. There's a lot more detail that we can go into with logarithms, but that's not a huge and crucial point to this course, the understanding logarithms. We're just using this button in our calculator, this function, as a tool to investigate exponential models. And we're going to start out with an example where we use a log function to solve the equation 5 equals 3 to the x power. 5 equals 3 raised to the x power. So what we do is we have that exponential term isolated. Okay, we would have to do some preliminary work if it wasn't. And then the fancy step that we're going to do here is we're going to take the log of both sides of this equation. So I'm literally just writing the word log next to the 5, and I'm writing the word log next to the 3 raised to the x power. And what we do next is we use the property from the previous slide, and I'm going to bring that exponent down in front of my log of 3 term. Okay, so that's the fancy step where we use the property. So we just write log on both sides, use the property from the previous slide, and now this is multiplication right there between the x and the log 3. And when we're solving equations, how do we undo multiplication? Well, we undo it with division. We're going to divide the right-hand side by the log of 3, and we divide the left-hand side by the log of 3. Cancel it out there, and we get x is equal to. Now, on your calculators, you all have a log button. For mine, it's right below the second button. So I'm going to type in the log of 5, close that parentheses, and then divide by the log of 3, and close that parentheses. Okay, and when I hit enter, I get 1.464, and then some more numbers. So I'm going to round that to x is equal to 1.46. 1.46. And so what that says is, in the original equation, if I raise 3 to the 1.46, etc., all those other numbers, power, I get 5. Okay, that's the equation that we have solved. Okay, so but make sure that you can find that button in your calculator, the log button, and understand how to use it, and don't forget to close the parentheses. Now let's go through our last example for this section, where we're talking about the doubling time for a population. We'll start out in 2016. India's population was 1.3 billion. Their growth rate, 1.2%. And we want to know, assuming that the growth rate stays the same, what year will their population double? Okay, so let me write the formula first that we need. A equals, keep doing that with a highlighter, A equals p times 1 plus r to the nth power. In this one, because they say in what year, we're solving for the exponent. That is our unknown, so we're going to have to use the logs on this one again. All right, but let's substitute in what we do know. We do know that their initial population at the beginning is that 1.3 billion. That's the p, the principal. Okay. Inside of the parentheses, we know 1 plus my growth rate is 0.012. 1.2% is 0.012. I'm going to keep the n as an n because I don't know what that value is. But what about A? We do know that. If we're being asked for their population to double, right, then A is 2.6. Now, how did I get that? Well, I took the 1.3 and I just doubled it. 1.3 plus 1.3 is 2.6 billion people. All right, so that's what we're looking at here. So to solve this equation, I can add what's in the parentheses, 1.02. So let's do that first. 2.6, 1.3, parentheses, 1.012 to the nth power. Here's where some students will make a mistake, so make sure you're listening to this step. Okay, do not distribute, do not multiply 1.3 and 1.02. That is not correct. This exponent, the n exponent is only stuck to the 1.012. It would be incorrect to multiply the 1.3 in. So what we do is we divide both sides by 1.3. Okay? That's how we undo that multiplication. 2.6 divided by 1.3 is 2. Hey, because we're doubling. The population is doubling. 2 equals 1.012 to the nth power. You can keep the parentheses or drop them off now. It's up to you. Now, to solve for the exponent, this is where we involve logs or logarithms. We're going to take, just like the earlier example, the log of both sides of this equation. On the left, the log of 2, and on the right, the log of 1.012 to the nth power. The property says that that exponent can come down, so the log, that's a terrible G, the log of 2 is equal to n times the log of 1.012. Divide both sides to get n by itself and undo that multiplication. 1.012, 1.012. That cancels out. I'm going to come up here for writing down my answer. And we get n is equal to, now again, I'm typing into my calculator, the log of 2, it's right below that second button, close the parentheses, divided by the log of 1.012. Close that parentheses. My calculator spit out 58.10, etc. And I'm going to round that to 50. Well, let's take a look at it real quick. If I go back up to the top, right? They're asking me, we're starting out in the year 2016, and they want to know, in what year will India's population double? Right? It's going to double after 58.1 years. So after the 58th year, it will not yet have doubled. So even though this number technically rounds down, I'm going to bump it up to 59 years, right? The population will double in the 59th year, and I'm going to write that down, okay, just so you have it in front of you. The population, the population will double during the 59th year. There we go, 59th year. Okay, and what year is that? Well, if I take 2016 plus 59, 2016 add 59, you get 2075. That would be the year. The year 2075. That sounds like so far into the future. But the population of India will double in the year 2075 compared to what it was in the year 2016, just 4 years ago. Okay, so that's how we use exponential functions and logarithms to investigate this idea of exponential growth. Not linear growth, not quadratic growth, but exponential growth. It applies to bank accounts, it applies to populations of people, populations of fish, all kinds of stuff. All right, thank you very much for listening. That is the end of this video. Work on that homework and let me know if you have any questions. Have a wonderful day.